This week in the Encrypted Economy, we start to explore the foundations of how the ability to secure data fundamentally changes the very economics of our society and the business, legal, and technical forces that are shaping that. To some, introducing concepts like we do here, relating to secure multi-party computations and homomorphic encryption, sounds like it might be the topic of academic research or just a security discussion. But it's so much more. Both of these terms relate to the ability to secure processing of data by its very design. And that opens up a whole world of what we can do with that data. Once you understand this, you can see that what we are really talking about are truly transformative forces for our society. We were really excited to have Hemenway Falk, a leading expert in applied cryptology from the University of Pennsylvania, on the podcast. We began with the basics of cryptography and privacy-preserving computations. Then we delved into practical applications that will shape the future of secure computing. From banks sharing security secrets to decentralized social science research to underwriting satellite collisions, I know you will learn just as much as I did, which is why I'm excited to share this latest episode of the Encrypted Economy. Be sure to keep an eye out for Brett's continued important work in this area and stay tuned for more great content from the Encrypted Economy. And of course, please subscribe to this podcast, share it with your friends, and review it. Welcome to the Encrypted Economy, where we look at the business of, regulation, and security for all things encrypted, digital assets, blockchain technology, privacy, and smart contracts. Hope you'll join us while we explore these forces that are shaping the economy. This is Eric Hess with the Encrypted Economy. I am excited to have Brett Hemenway Falk with us today. He is an assistant professor at the University of Pennsylvania, has done a lot of publications in the field of cryptology, a focus being multi-party computation, but also covers a lot of other areas such as privacy. And he really is what you would call an applied cryptologist. He works in the space. He's not just theoretical, which makes him a great guest to have on the show talking to this audience. Brett, thanks so much for joining us. I'm really excited to have you on the show.
Yeah, thank you. I'm excited to be here.
My introduction probably didn't do justice. Could you give us a little bit of background on what you do and also how you got here? What drove you to be the mathematician, researcher, cryptologist that you are?
I got a PhD in mathematics at UCLA, and when I started there, I thought I really wanted to do research in pure mathematics. But while I was there, I got hijacked and I learned a little bit about theoretical cryptography, which is highly mathematical these days, and it was much more exciting and fast-paced than more traditional mathematics. And I think part of the reason is that it's a much newer field. There's been really good mathematics done for the last maybe 3,000 years, but there's only been really good sort of mathematical cryptography done for the last 40 years or so. And so there's a lot that people still don't understand. Whereas in math grad school, you can learn these proofs that are 300 or 400 years old, and it takes 3 years into grad school to learn enough background to understand these proofs. Whereas in cryptography, your first couple months in, you can get to the forefront of the field and start actually making real contributions. So I was really excited by a lot of that. And when I got my PhD, I did a postdoc also actually in math for 3 years at the University of Michigan. And from there, I got a research assistant professorship at University of Pennsylvania. And so I'm now in my 7th year at Penn. But at Penn, I've slowly shifted towards more and more applied uses of the more traditionally theoretical cryptography. I think it's really interesting to look at a lot of the new applications that are being developed by academic cryptographers and how they can be used and how they fit into real world models. And so, as you mentioned, a lot of my research is in this area called secure multi-party computation. And the core goal there is to allow a group of sort of mutually distrustful people to collaborate and cooperate in a way that they couldn't do without some kind of cryptography or without some kind of trusted third party. And the goal of the cryptography is to essentially allow them to cooperate without requiring them to have some mutually trusted outside party.
So Brett did a great podcast with Appetite for Disruption with Troy Paredes and Lee Schneider on some very basic components of cryptology. It's a great resource, and we're going to move maybe a little deeper into it. And to do that, we're also going to go through a speed round, which Brett has consented to ahead of time. So we're putting Brett on the spot. We're going to cover a lot of ground, and then we're going to go a little deeper. And Brett can call me out and say, this isn't working for me anytime he wants. So speed round, the difference between symmetric and asymmetric encryption.
Symmetric encryption is what most people think of, I think, when they think of encryption, and it dates back literally thousands of years. And the idea is that if you and I want to communicate in secret, we have to share some secret key. And all of the privacy we get is from the fact that you and I both know a secret key that is unknown to any eavesdropper who might be listening in on our communication. And so in order to understand the communication, you have to have this secret key. Asymmetric cryptography is a much newer invention. It dates back only about 40 years now. The idea there is that you have a key pair, and the key pair consists of both an encryption key and a decryption key. And you use the encryption key to encrypt messages and use the decryption key to decrypt messages. And public key cryptography solves one big problem of symmetric cryptography or private key cryptography, which is key distribution. So if you and I require a secret key in order to communicate, how do we get a secret key that's shared between us? And that's a big problem on the web, right? If I want to encrypt my transactions when I buy something on Amazon, I don't want to have to go to Amazon's headquarters and share some secret key with them before I can purchase from their site. And so public key cryptography solves that by doing things asymmetrically, that you don't use the same key to encrypt and decrypt. You use one key for encryption, one key for decryption. So I will generate a key pair and you will generate a key pair. And when I want to send a message to you, I will encrypt it with your public key, which allows me to encrypt but not decrypt. And when you want to send a message back to me, you will encrypt it with my public key, which allows you to encrypt to me but not to decrypt messages from me.
Okay, leading me to my next speed round question. 3 core components of an encryption platform.
I think we're talking about basically key generation is when you generate the actual keys, and then encryption and decryption. And these are the 3 fundamental algorithms that correspond to most crypto systems that are designed at building private communication.
All right. Definition of zero-knowledge proof.
Okay, so zero-knowledge proofs are actually very interesting mathematical objects, and they've been around in the crypto literature for actually decades, but they're getting a lot of popularity now, and I think a lot of that pressure is from the blockchain space. But the idea of a zero-knowledge proof is to allow me to prove to you that I know something without revealing exactly what it is. And so there are a lot of applications for zero-knowledge proofs. One of the first applications was actually in authentication. And so this is an easy way to understand it, I think. Imagine that you want to authenticate yourself to a server. Right now, the way you do that is with a password. So if I want to prove to Gmail that I should have access to my Gmail account, I give them my password, and that's how they know it's me. But what if somebody pretended to be Gmail, and they say, "What's your password?" If I just blindly give them my password, all of a sudden they have my Gmail password and I've revealed too much information. So what if I could prove to Gmail that I know my password without revealing what that password was? If I could prove using zero knowledge, and zero knowledge means that I prove to you that I know something, but I prove zero additional information. There's no extra information beyond the fact that I prove to you that I know it. So if I could prove to Gmail that I knew my password without telling what my password was, then any eavesdropper who might be listening or intercepting that password or pretending to be Gmail actually couldn't use my proof to pretend they were me in the future. And now, in the blockchain context, there are a lot of other applications of zero-knowledge proofs. And one core application is in proving that transactions are valid. So blockchains, even though they're built on cryptography, really don't offer very much privacy. And the reason they don't offer very much privacy is because they require that these public validators validate every transaction. If I want to make a cryptocurrency transaction, I submit it to some validators, and these miners have to check that this transaction is valid, that the coins I'm spending haven't been spent before, that my account has some balance in it, which requires them to know what coins I'm spending and how much and who I'm sending to, or what my personal account is. And so I don't have a lot of privacy on that standpoint because the validators need to be able to check if the transaction was valid. But what if I could encrypt my whole transaction and then prove to the validators that the transaction was valid without revealing any information about the transaction itself? And so this is exactly what zero-knowledge proofs allow you to do. They allow you to prove that something is true without revealing information about it. And so like one way to think about this in a blockchain space is that you can encrypt everything you're doing and then prove to somebody that what you did was all right. Even though everything you did was encrypted and in secret, you can prove that those encryptions correspond to what they should have been. I can prove to you that my transaction was valid. In terms of credential management, people have been using zero-knowledge proofs to prove credentials. So if the DMV gives me a driver's license, and imagine they give me a digital driver's license and it was digitally signed by the DMV, and now I want to go to a bar and prove that I'm over 21. I don't want to show them my whole driver's license because that reveals my name and my weight and my address, but I just wanted to prove I'm over 21. I could use a zero-knowledge proof to prove that I have a driver's license that was signed by the DMV, and that includes a date of birth that puts me at over 21 years old without revealing any of the underlying details. So I can prove that I have the credentials to do what I'm supposed to do without revealing those credentials or anything more about them.
Brett, what is homomorphic encryption?
So homomorphic encryption is a way to encrypt messages so that you can actually compute on the encrypted messages and have those computations pass from outside the encryption to inside the encryption. So it allows you to do computations on private data without having to ever decrypt the data. And the simplest way you can think about it is if I have two encrypted messages and I want to get an encryption of their sum, that there's some way to take the two ciphertexts that are encrypted and put them together so that I have an encryption of the sum of the two plain texts. Or similarly for multiplication, if I have two encrypted numbers and I want to be able to get an encryption of their product, I can then combine these two encryptions to get an encryption of their product without ever decrypting in the middle. And if I can do that for addition and multiplication, I can put those addition and multiplication operations together to get more and more complicated functionality. And in principle, I could take some encrypted values and run arbitrary computations on the encryptions and get an encryption of the result without having to decrypt in the middle. And so there's strong applications for this around outsourced computation. So if I wanted to use something like AWS to compute on my data and do machine learning on my data, in an ideal world, what I could do is I could encrypt all my data and send it up to AWS and have them compute only on the encrypted data and never decrypt anything, and then give me back an encryption. And even though they had created this encryption, they themselves couldn't decrypt it. And then I wouldn't have to worry that AWS sysadmins or somebody else on the way might ever see the data while it was decrypted, because it was never decrypted off of my machine.
So what's commonly known is encryption at rest and encryption in transit. Is homomorphic encryption the last mile?
Yeah, in some ways, homomorphic encryption goes beyond encryption at rest and encryption in transit. It gives you encryption under processing. And that's a really exciting thing, because really traditionally the best practice was if I wanted to use some cloud server, I would encrypt in transit. But once the data got there, they would have to decrypt it in order to work with it. And so the idea of using homomorphic encryption is really that you never have to decrypt the data until the very end.
So what's the primary limitations for the adoption of homomorphic encryption, and how do those limitations differ from something like multi-party computation?
So one of the primary limitations of homomorphic encryption has been that it's been very computationally intensive. So what that means basically is that if you had some computation that you wanted to do and it was going to take your computer a few seconds of computation time to do it, if you then wanted to do that same computation but do it on top of homomorphically encrypted data, it would take you maybe 10,000 times longer. So instead of taking your computer 1 second, it might take 10,000 seconds. And for some applications, that's okay. But for some applications, that's not okay. If your computation was going to take you a week of AWS time and now it takes you 10,000 weeks, that's not really acceptable anymore. But for some computations, if it was going to take a second and you didn't need the result for a couple of days, it's no problem to have a 10,000-fold increase. So that's been one barrier to adoption. And right now, what that means is that this fully homomorphic encryption is only useful for certain types of applications where you don't need the answer in real time, maybe, or the computations aren't too big. Basically, you can't do something if your computation was so expensive that it was on the border of practical anyway, you can't do it under fully homomorphic encryption right now. But Beyond that, as homomorphic encryption has gotten to be more practical, and there are now a number of libraries that actually allow you to do this. So IBM has one that's called HELib, the Homomorphic Encryption Library, and Microsoft has one called SEAL. And there's a few companies that are built around actually providing homomorphic encryption services. One of them is Duality, and they have a nice homomorphic encryption library called Palisade. And another one is Infer with a PH, and they have a nice homomorphic encryption library called TFHE. But one of the problems with this is that even though the libraries provide a nice interface to homomorphic encryption, then any kind of things that you want to build on top of that, if you wanted to do machine learning on top of that, you couldn't use a traditional machine learning library. You'd have to implement whatever types of machine learning algorithms you wanted on top of this library. You can't just plug it into an existing thing. If you were going to use Python, like SciPy or something, to do some statistical analysis, you can't just run SciPy on top of this fully homomorphic encryption. You'd have to re-implement your linear regression on top of fully homomorphic encryption. And so that's what some of these companies do for you.
That's a very important point. So when you're trying to implement a homomorphic encrypted environment, you need to basically build your applications to support homomorphic encryption by design, because there's just no natural plugin.
Exactly, yes. So you have to redesign a lot of things from the ground up. And that is a big barrier to adoption right now. And so the two big barriers are that it's much slower, which is basically a deal breaker in some contexts, but not a problem in other contexts. And then the other big thing is that basically you have to redesign your software from the ground up to use these homomorphic encryption libraries.
Let's shift gears to your true love, which is MPC. So you've done some recent work there. It looks like some exciting work in the way that you've designed to be privacy resistant and to facilitate those multi-party computations. Is it a lesser computational load? Is the need to ensure that your supporting infrastructure application systems are able to support MPC? Does that kind of experience the same kind of issue or at a lesser scale as homomorphic encryption?
Let me just give a quick background on secure multi-party computation, or MPC, is the idea where you have a group of people who all have their private inputs and they want to compute some joint function of their inputs and they want to get some output, but they don't want to reveal any intermediate steps of the computation. They don't want to reveal their private inputs to each other, and they don't want to reveal any intermediate steps to anybody else. And so you could imagine joining different data sets. And Google has some nice examples of this about looking at privacy preserving ad conversions. So for example, Google knows whether you've clicked on an ad off of the Google search page, and Visa knows whether some person has actually completed a purchase once they've gone to that site. And if you could combine those two pieces of information, you could know whether this ad click actually was converted into an actual purchase. And that's something that advertisers would really like to know. But Visa doesn't want to give out its data of who's purchasing what at what times, and Google doesn't want to give out its data of who's clicking what at what times. If you anonymize these data first, then you actually can't link them. And so the question is, how can you do this privacy-preserving data mining when you have multiple participants now who all have their private data? And this is exactly what secure multi-party computation is designed for, to say, Google has some private ad click data and Visa, say, has some private purchase data. And can you link them and do some statistics? Could you do a linear regression on top of this? Or could you do some machine learning? Or could you even just do simple things of like counts by category? And secure multi-party computation allows you to do this. In government applications, there's a lot of questions about, you have allies who want to work together to complete some mission, and they want to work together, but they also don't want to reveal all of their military capabilities to each other. And so how can they work together in a way that allows them to compute tactical ideas without revealing all of their underlying capabilities to each other? So secure multi-party computation allows you to do this, and it's a cryptographic protocol for multiple parties. Whereas fully homomorphic encryption often is in the case where you have a single data owner who wants to outsource data to somebody else. But they both allow you to do kind of encryption computations on private data. And right now, the technology is such that fully homomorphic encryption tends to be a little bit faster, I'd say by about tenfold. So instead of being 10,000 times slower than a native computation, it's only 1,000 times slower, or maybe even a little less than that. It does have the same problem that fully homomorphic encryption has, that if you want to actually do some computations privately, you pretty much have to build your software from the ground up to actually use secure multi-party computation. The software doesn't just plug in naturally into some whatever machine learning library. And so right now, most of the secure multi-party computation applications that are being developed, they're being developed as custom one-off things there. So they're private companies, again, that will build you secure multi-party computation platforms for the specific types of computation you want to do. I do some consulting for a company called Stealth Software that their primary business is building secure multi-party computation software. There's a company, Partisia, does this, and Unbound Tech does this. And so they're starting to get into practical applications, but you still need to develop your software from the ground up. And so, again, there are lots of really interesting use cases. In the healthcare space, for example, if you have different health insurers and the way the health system is set up in the United States, you probably change insurers a lot. When you change jobs, when you graduate from school, if you move to a different state, you probably change who your health insurer is. And when you change health insurance, your new insurer doesn't have easy access to all of your old health records. And so if an insurer wants to do some statistics and they want to say, did the preventative procedure we gave you when you were 18, did that reduce your risk of cancer when you were 50? The insurer who has your health records from when you were 50 probably doesn't have your health records from when you were 18, and that's held by somebody else. And so as a whole, the group of insurance companies would like to be able to link these data to do a lot of basically statistics on this to look for long-term trends. And again, if you anonymize the data first, then you actually can't link it. And that's exactly what you need to do, is you need to be able to link it if you want to run some statistics on it, because you need to know is the same person that you gave a preventative treatment at 18 was the same person who you didn't have to treat for cancer when they were 50. And you can use secure multi-party computation to do things like this. At Stealth, we've been working on a project actually to do this for a lot of education outcomes. So you imagine you have a system where you have lots of schools and they have information about their students, about what their GPA was, what their major was, and you want to link this to outside outcomes. What salary did they get afterwards? And the schools don't want to release the student data, and the Social Security Administration, which has some information about your salary afterwards, can't just release data about people's salaries, but you'd like to know general information about which salaries end up with the most money afterwards, or which schools give you the best return on investment or something like this. And you can actually do these secure computations on this kind of data where you have maybe hundreds of schools who all have their own private data and they don't want to share the data with each other or with anybody else.
So would MPC be well suited for something like vaccine research, particularly where you have a number of pharmaceutical companies that are competitors, but also trying to achieve the same end result, like in the case of coronavirus?
Yeah, so I think right now, no one is implementing this kind of thing for virus development. I actually don't know enough, I think, about the development pipeline to say exactly what steps this could be used for. I would say that there are a lot of applications where there are competing companies that essentially don't want to share some underlying data, but would benefit from overall market data as a whole. So one application we looked at somewhat was in insurance. And so again, not for health insurance, but actually for insuring rare events. So if you're an insurer we talked to some satellite insurers. So you insure someone's satellite in space, and satellites are extremely expensive. And so if you're an insurer, you're on the hook for tons and tons of money up there. But satellite crashes or total destructions are fairly rare. And so as an insurer, how do you set your rates? Because you actually don't have that many data points, right? You don't know about your own customers, but you don't know about all of the customers as a whole. And so if insurers could essentially share data to compute aggregate statistics to say each insurer has private information about how many customers they have and what their satellite setups are and how often they make claims, then they could do some global statistics on these claims data and get more information than any one individual could get by themselves. And they could all benefit from this, even though they are nominally competitors. So there's a lot of applications like that. Another application that's very similar is, this time it is viruses, but computer viruses and hacking. Banks are worried about cyber attacks. And the issue is, if one bank is hit by a cyber attack, probably many of the other banks are at risk because they're using similar software, they have similar kind of vulnerabilities, but no individual bank wants to reveal anything about the cyber attacks that they're experiencing, mostly because of bad PR, that if you have a lot of attacks, you don't want to just tell all your competitors, hey, I had this many attacks and somebody got in because they exploited this specific vulnerability. But the community as a whole would really benefit if you could have some essentially like privacy preserving database that would allow people to say, here's how many attackers exploited this type of vulnerability. And so we need to be worried about this. If you could have global risk statistics about cyber attacks. And so this is another place where you have competitors who are business competitors who really need to work together a little bit. And without some kind of external privacy preserving tool, they're not able to work together in that way.
Would that work with a centralized database or a decentralized database?
So one thing about secure multi-party computation is basically the idea is to eliminate the need for a centralized party. So almost all these applications, if you had a totally trusted centralized party, you wouldn't need cryptography very much at all anyway. So if you had a bunch of banks that wanted to learn global information about their cyber attacks and they had a trusted government entity or some trusted non-government entity, they could all just give all of their data to this trusted party, and the trusted party could compute some global statistics and then delete the raw data underneath and then publish a report saying this is our global statistical summary. But in a lot of cases, it's really hard to find this trusted party, sometimes because there's nobody that everybody trusts together. Sometimes actually, even if there's somebody that everyone trusts, that person doesn't want the responsibility of holding everybody's sensitive data.
We were talking about the differences between centralized and decentralized computations and the value of secure multi-party communications in terms of establishing a decentralized, effectively, I don't know if I call it a protocol, but a decentralized platform. You can correct me.
Protocol or platform, people use both terms.
Okay.
And actually, I think the question about centralization versus decentralization, there are actually two important distinctions about that. One is the centralized party trusted? Meaning, can you trust them to always do the right thing? And the second is, do you want to keep privacy from the centralized party? And these are actually two different things. You can have one but not the other, or you could have both. And so again, like thinking of the blockchain space, which has made the word decentralization really a buzzword these days, blockchains are not about decentralizing privacy. So again, I would say that blockchains like Bitcoin or something, they are not designed to improve your privacy. And even in the original Bitcoin white paper, Satoshi Nakamoto basically says, actually, the traditional banking system is all right from the privacy standpoint, because although you don't provide privacy from your centralized party, if I use Bank of America knows all my transactions, but they don't share that with anybody else. Whereas with the Bitcoin platform, where you've decentralized the ledger, now that ledger is available to everybody. And so everybody can see every Bitcoin transaction. And now it's true those transactions are pseudonymous. It's not associated with my name. Brett does not appear on the blockchain, but every transaction that's ever occurred on Bitcoin is publicly available. And that's not true in the traditional banking system. It's not like Bank of America scrapes off my name and then posts every check that's ever been run through it. Whereas there's another question, which is basically, are you sure that the centralized party is going to do the right thing? Basically, are you worried that the centralized party is going to somehow cheat you? So like Bitcoin was designed around this libertarian idea that they were worried that banks were going to censor transactions, right? That if you are put on a terrorist watch list or something, your bank will probably just freeze your bank accounts. Or if you set up a website that's selling copyrighted things and you get a takedown notice, PayPal may just shut down your account and freeze all your assets. Whereas in Bitcoin, because it's decentralized, there's no method for this centralized kind of shutdown. And so secure multi-party computation is aimed at actually getting at both sides of these things. So getting at both the privacy, can you provide privacy from the centralized party? And then because it's decentralized, you have decentralized control as well, so that nobody can kind of change the state of the system or update the database or run computations that the majority of the participants don't want you to run.
The other challenge, obviously, with the centralized computation is when you get into things like oracles. So if you have a centralized oracle and the oracle is itself compromised or manipulated, once that oracle is corrupted, it could impact all the other parties that are dependent on that centralized oracle. I think it boils down to that you need a very robust centralized oracle, meaning there has to be a lot of computation to minimize that risk. You have to have a lot of security controls. Or if it doesn't have those controls or it's easily manipulated, then the decentralized oracle is probably a better use case. And maybe that ties right into the whole secure multi-party computation. Why don't you take a second to define oracle?
In the blockchain space, blockchains themselves know everything that's happening within their blockchain, but they really have no idea of what's happening outside. Like the Bitcoin blockchain was made to track the ownership of Bitcoin tokens, but it has no connection to the outside world. It knows nothing about US dollars. It knows nothing about whether it rained in Massachusetts today. It knows nothing about the stock market. It knows nothing about other cryptocurrencies like Ethereum. Anything you want to do to interact with the real world, if you wanted to buy Bitcoin using US dollars, the Bitcoin platform itself doesn't do that. You need some external party. If you want to make, say, something like an insurance contract, and you want that insurance to get paid out based on some real world event, you want to get flight insurance and you should get paid if your flight is canceled, the Ethereum network knows nothing about whether your flight was canceled. You need some interface, and these interfaces often are called oracles. If I write an insurance contract that is going to pay you if your flight was canceled, we need some external party, some oracle, to tell our contract whether the flight was canceled or not. And essentially, I write my smart contract and I say, I don't know what's happening in the real world, but we're just going to trust this oracle. And I bake that trust right into the smart contract. I say, your flight was canceled if and only if I get a signed message from this oracle that says your flight was canceled. That works, and people do that, and there are oracles for all kinds of things. Anything you might want to bet against or insure on, you can find some oracle who will provide the service of telling you whether that happened or not. But the problem with that is you've lost a lot of the benefits of decentralization. Why did you spend all of this time and effort to write a decentralized insurance contract instead of using a traditional insurer? Well, the reason was because you wanted some decentralization. But now, although your contract is decentralized, whether it's actually paid out is held in the hands of a single centralized party. And if they decide to cheat you, well, too bad for you. Or if they are corrupted, well, the contract is going to pay out whether the real event happened or not, because the contract knows nothing about the real world. It just knows whether it got a signed message from this oracle. This is actually a big fundamental problem in the blockchain space, is how do you interact with the real world? And the on and off ramps tend to be very centralized. Oracles are one place of centralization. Exchanges are another place of centralization, which is basically how do you convert fiat currency like US dollars to cryptocurrency? You need some external party to kind of do this, because the blockchain doesn't know anything about US dollars. You can't give US dollars to the Bitcoin blockchain in any way. There's no method for buying Bitcoin. Any exchange that allows you to buy Bitcoin is probably some centralized entity sitting off of the chain that you give it US dollars, and maybe it gives you a secret key to an account, or maybe it makes a transfer on the blockchain. But that's a centralized place, and there's a lot of risks to centralization. Exchanges can freeze your accounts just like traditional banks can. Exchanges are centralized places that are vulnerable to hacks. If the exchange is holding billions of dollars in cryptocurrency, it's a really high value target, and a lot of exchanges have been hit by hackers. This type of centralization is a big problem. There's a question basically from both the security side, but also from the ideology side. Bitcoin maximalists say decentralization is good just for decentralization's sake. And why should we be using all these centralized parties? The centralized parties are risky, they can cheat you, and they immediately form some kind of oligopoly, which is not good for fairness and democracy. So you can believe these arguments or not, but a lot of people are pushing for kind of a decentralization. And so one question is, how do you decentralize these kind of things? Like, how do you decentralize an oracle, or how do you decentralize an exchange? And it's a challenging question. So one simple way to decentralize a lot of these kind of oracles, you actually don't need the full power of secure multi-party computation. You can use a simple kind of threshold scheme. So suppose I want to, again, have some kind of insurance contract, which is going to ensure me that if my house is flooded, I get paid some number of ether. I can write this contract, but instead of relying on a single oracle to tell me whether my house was flooded, I could say, well, here are 10 oracles, and as long as 7 out of 10 sign a message saying your house was flooded, then you get paid. And I can write that functionality right into the smart contract. Now I have multiple oracles and I can do a kind of majority vote of them because I didn't need any privacy from the oracle itself. And people have done some work to try to decentralize exchanges also, again, kind of without secure multi-party computation, right? DeFi and DEXs are really popular on Ethereum, and you can write these smart contracts which act as exchanges, but they're pretty much tied to a specific network. My smart contract is still limited to Ethereum. I can't trade Bitcoin with a contract that's sitting on the Ethereum network because Ethereum doesn't know anything about Bitcoin.
So you're making a compelling case for not using secure MPC. So good
No,
job.
No, so I'm not saying, I'm saying that people are doing all these kind of things and they're not using MPC for this. But that's not to say that you couldn't use MPC. So what I'm saying is, okay, so in the blockchain space, people are just doing whatever they can think of fastest. And one of the things that's really exciting about it is it's pushing them to roll out new technology in a way that I think wouldn't have happened if it weren't for this crazy speculation around cryptocurrency prices. It's been, as you push traditional cryptographic ideas like secure multi-party computation, companies are very slow to adopt things. And in the blockchain space, people will adopt whatever technology they've heard of. They can hear of it once and they're just like, okay, we'll throw millions of dollars at it immediately. And that's not to say it's a good technology. Some of the technology is amazing,
but there are shortcuts.
Some of these are shortcuts. Some of them have actual like real drawbacks. So again, like just to make a comparison, if you have the way DEXs or decentralized exchanges are made right now, if they are written as a smart contract on the Ethereum blockchain, you're limited to the Ethereum ecosystem. You can't talk across chains in any way. And people have tried to get around that by saying, well, we can take wrapped Bitcoin. What is a wrapped Bitcoin? It is a token on the Ethereum network where some centralized party promises you can exchange this wrapped Bitcoin for a real Bitcoin on the original Bitcoin network. But you have a centralized party of exchange. And if that centralized party actually says, I don't feel like redeeming your wrapped token, well, now your wrapped token has no value, right? But this is a workaround to allow you to use these DEXs. Whereas in principle, you could use secure multi-party computation to build a truly kind of cross-chain decentralized exchange. So you could say, we take 10 servers and they sit in different countries and are owned by different companies or something and are kind of decentralized in some way. And these servers will jointly compute a secret key pair for an account on Bitcoin and for an account on Ethereum. And now these servers will take buy and sell bids, and they execute a multi-party protocol to do atomic swaps, where essentially you make a swap on the Bitcoin network if and only if you make a corresponding swap on the Ethereum network. You can do this outside of all the blockchain space, or you can do it within a blockchain. And there's actually some really cool work coming out of Algorand looking at using secure multi-party computation within the Algorand blockchain to allow the blockchain itself to keep a secret. So basically, one of the problems of blockchains is that everything on the blockchain is public. You can't have a secret key on a blockchain because everybody can see all the information on the blockchain. So like a smart contract can't have a signing key built into it because everybody can look at the code from the smart contract. And that really limits smart contracts. If you could have a decentralized way of storing that secret key in a decentralized way among all of the different miners or validators in the system, then you could have a smart contract that actually signs messages as coming out of that smart contract. And that secret key would be decentralized among the whole blockchain. And that would give you a lot of extra functionality, including the kind of functionality you'd want of being able to do cross-chain transactions. So that's one thing that secure multi-party computation can do that this traditional like decentralization via smart contract can't do.
Interesting. So it sounds like one particularly compelling application could be a derivatives market that's off-chain.
So you could have a decentralized way of wrapping Bitcoin. So now I say I'm going to choose 10 servers and they generate a Bitcoin wallet and they have a bunch of Bitcoin in it. And now those servers engage in a multi-party protocol to create wrapped Bitcoin on Ethereum. You could do this. And then you guarantee that as long as the majority of those servers are uncorrupted, you could always redeem your wrapped Bitcoin for the true Bitcoin that are held in the wallet that's distributed among these 10 servers. So yeah, you could have much more decentralization in a derivatives market.
Now, do you think that platform would be robust enough to do things like trade surveillance or that kind of thing?
So this is one of the other things that's very cool. Since secure multi-party computation is very flexible, you can get all kinds of privacy-preserving surveillance on top of that. So again, secure multi-party computation is a little slower than doing things in the clear. Depending on what your transaction volume was, you might have some issues, but you can actually, in principle, do complete surveillance over privacy-preserving transactions and queries. Outside of the blockchain space, one of the projects I worked on was actually building a traditional database system like this, where you have a database that's decentralized among a fixed group of servers. And you do this partially for robustness so that if some of the servers are compromised, the data isn't lost. But if you do this using traditional replication, if one of the servers is penetrated, then all of the data is compromised. If you have 10 servers and you've replicated your data 10 times in order to get robustness against crashes, if somebody breaks into any one of the 10 copies, they can steal the whole database. So you can do this cryptographic secret sharing where the data is split among the servers. And now if any small subset of the servers is compromised, they learn absolutely nothing about the data. So it's not like they learn some fraction of it, they learn nothing. And then people can make queries to this database. And now you might also want to make the queries themselves private because the queries might leak information about what you're interested in. So if this was a database of classified material or something, the queries you're making reveal some information about what you're looking for. But now if you keep the queries private, there's another question of how do you ensure that the person who's making the queries is authorized to make these queries? So how do you have access controls and policy controls in place when everything is private? If you build your whole system using secure multi-party computation, you can actually have the best of both worlds. You can have private queries and you can have these really strong and robust access controls that people can only make the kind of queries that they're authorized to make without actually revealing what the queries are to any trusted auditor or regulator. If you imagine translating this to the blockchain space, you want to say what we have is maybe like some kind of privacy preserving transactions where not only you have to check if the transactions are authorized, but also maybe you want to check on top of them that they correspond to some kind of regulations without violating the underlying privacy.
Great. I could do this for hours, honestly. This is exciting stuff. I'm going to press a little bit further. So I'm going to have to go back to my lightning round because I'm going to introduce more vocabulary. Explain the difference between deterministic and probabilistic.
A function is deterministic if every time you give it an input, it gives you the same output. And a function is probabilistic if every time you give it an input, it gives you different outputs. And the reason why probabilistic things are so important in cryptography, one reason at least, is comes back to the notion of public key encryption. So if we have a secret key encryption scheme, encryption and decryption requires the same secret key. Encryption can be deterministic, that if I have a secret key, my encryption function can take my message and my secret key and munge them together in some complicated way. And if I encrypt the same message, maybe it will always encrypt in the same way. But in a public key cryptosystem, you actually cannot have a public key cryptosystem that's deterministic, that's also secure. And the reason is because the public key, which is public, allows anybody to encrypt. So if I encrypt some message that I say, you ask me, do you want to go to the movies? And I encrypt a message and I send it to you. If my encryption were deterministic, anybody with my public key, which is everybody because I broadcasted my public key, can encrypt yes and see if that matches the ciphertext I sent you. And they can encrypt no and see if that matches the ciphertext I sent you. And they can then figure out which message I sent by just running a bunch of encryptions and matching the ciphertext they come out with. Public key encryption has to be probabilistic, which means that every time I encrypt a message, I generate a new random nonce and I encrypt that with my message. So every time I encrypt a message, it encrypts differently. And that prevents against these kind of brute force attacks.
In terms of the output that you get from secure multi-party computation, there's probabilistic in terms of security, but there's also probabilistic in terms of the outcomes you're trying to achieve or the computations you're trying to conduct on it. Where does secure multi-party computation really hum. Do you see it as being useful for where the output is based on probabilistic computations, or given the computational limitations, deterministic?
You can use secure multi-party computation to securely compute deterministic functions or to securely compute probabilistic functions. And you can do them both about as efficiently, one versus the other. Though the one place where it actually matters is in the notion of security. Secure multi-party computation gives you a very strong notion of security, which says that when you run this protocol, and as part of this protocol, people are sending encrypted messages back and forth like crazy. And at the end, they get some output. And that output is something that they wanted to learn. And secure multi-party computation says when you run this protocol, you learn nothing more than the output alone. But what it doesn't say is that the output might give you too much information. If the output alone reveals a lot of information, that was your choice in defining the function that you wanted to compute. One nice example of this is one of the early applications of secure multi-party computation that I worked on was computing satellite collisions. You have satellites in space and their operators are worried that they're going to collide. And the problem is they don't want to share their private orbital information with each other. You'd like to have a way that two satellite operators can compute the probability that their satellites are going to collide without having to reveal their orbits to each other. And it turns out that you can look in the sky using like ground-based telescopes and look where satellites are, but the telemetry that you get from the ground-based telescopes is not high fidelity enough to actually compute the probability of collision. The private data is the really high fidelity orbital information that's being provided by the satellites themselves, and that's known only to the satellite operators. So we created a secure multi-party computation that allows operators to input their high fidelity orbital information and computes the probability of collision. And at the output of it is it spits out a probability of collision. The guarantee of secure multi-party computation is that the operators learn nothing more than the probability of collision. But the probability of collision itself reveals some information. That's within the model of secure multi-party computation. It says you asked to know whether your satellites were going to collide, and we tell you without any errors on that. We'll compute the exact function that you would have computed in the clear. But if the output alone reveals too much information, that's not within the purview of secure multi-party computation. That's something that when you're developing an application, you have to think about. One reason why you might want to compute a probabilistic kind of functionality is that if you're worried about this kind of inference, if the output alone reveals too much information about what you were computing, then you might want to add some noise to the output to basically prevent people from making inference. And this is a different field of security, basically, that goes under the name of differential privacy. And secure multi-party computation and differential privacy actually get at totally orthogonal aspects of the problem. Secure multi-party computation says, how can you compute the function and get the right output with no noise? But how can you do that computation in a privacy-preserving way? And differential privacy says that assuming you had some way to compute this function, how do you add a little bit of noise to it so that people can't infer the inputs from the outputs? You can do one or the other, or you can actually put them together, and you can use secure multi-party computation to compute a differentially private function, which means that the actual function you're computing is randomized, and that extra random noise you're adding prevents against reverse inference from the outputs to the inputs.
Is that a form of collusion resistance? Different.
No, so that's kind of different. So when you talk about secure multi-party computation, often the security is defined in terms of some kind of collusion resistance. What that means is that if I have 10 people who are participating in a multi-party computation, how many of them have to get together and collude against you in order for them to violate your privacy? So imagine you have a group of banks that are worried about cyber threats, and they want to compute some aggregate statistics about how many cyber attacks they've experienced. And now, as an individual bank, I want to know how many of these other banks, so I'm sending messages to all of them as part of this protocol, how many of them have to collude against me before my privacy is violated? And you can have secure multi-party computation protocols that provides a maximum level, which we would call like n-1 out of n privacy. So if there are n participants, even if everyone else colludes against you, they still can't trick you into revealing any extra information than they would get from the output of the computation alone. But some protocols only provide security against an honest majority. So in the case of 10 people, if 6 of them decided to collude against you, then they could break the security of the protocol. But those 6 people would have to work together and share all their information among themselves and share all of the encrypted messages they received and put those all together in order to infer some information about you. This collusion threshold or corruption threshold measures how many people have to work against you before your privacy is violated. From a privacy standpoint, you would always want this maximum level of collusion resistance, which is like n-1 out of n, which is even if every other participant in this protocol colludes against you, they can't violate your privacy. But it basically is more computationally expensive to do that. The protocol is slower if you want that level of privacy. So people will often compromise and say, actually, we will only give you security as long as no more than 2/3 of the people collude against you, or as no more than half of the people collude against you. And in a lot of situations, that seems pretty reasonable. If you have 10 banks, the idea of 5 of them joining together in a cabal to violate your privacy seems unlikely. But that's a distinction you have to make when you're designing one of these secure multi-party computation protocols. And they're theoretical algorithms that can give you any level of collusion resistance you want, but they have different performance trade-offs. You just have to trade off performance versus privacy there.
And what's the distinction then between that and differential privacy?
Differential privacy mostly comes in after the computation has been done and you get the output. So now, again, using a running example of trying to look at cyber threats for banks, the output of the protocol is how many banks using Windows 10 had intrusion in November or something. And if you happen to know that only one bank is using Windows 10, and that the output of this protocol says that one bank suffered an intrusion like this, now you can infer which bank that was because you have this outside information that says there was only one bank using Windows 10, and the output of the protocol revealed that there was one intrusion here. That kind of inference is okay in the model of secure multi-party computation because it says you reveal no more information than the output of the functionality alone, but the output alone maybe reveals too much. But that's considered separate. That's a separate question. And differential privacy says, okay, how much noise would we have to add to things in order for the output itself to hide the information about the underlying participants? It would add a little bit of noise to the counts of cyber incidents, and you wouldn't get the exact numbers. But now, because it added this random noise, you wouldn't be able to necessarily infer information about which incidents corresponded to which people based on the outside information you might have. Actually, right now, it's very cool that the US Census has started saying that they're going to release some differentially private data because you want to, census data has lots of information about individuals and you'd like to be able to do aggregate statistics around them. But if you reveal information about communities that are too small, it actually reveals information about individuals. The census is not worried about secure multi-party computation. The census itself is a trusted party. It gets all of the raw census data in, and it computes the true counts for every geographic area. And then it wants to release that data. And before it releases that data, it wants to add a little bit of noise. And the tricky part is to add noise in such a way that the noise is small enough that it doesn't screw up your statistics. So any statistics you do on the data that the census released should be approximately correct, whereas it should be enough noise that it hides information about the individuals. This is the trade-off of differential privacy. Whereas computation would be something like saying, imagine we didn't have a centralized trusted census, right? If you don't trust the census with the raw data, could you compute the aggregate statistics without actually giving the census the responses on the census forms, but having that computation done privately?
Wow, that's a lot to think about. What projects are you working on now? Or maybe even more specifically, what projects are you hoping to work on that you really juice, that you're like, wow, this would be really great to delve in deeper, and it's an exciting developing area?
So I think there's really a lot of room now for developing new applications of secure multi-party computation. And I mentioned a little bit, one of the projects that I've been working on for Stealth Software is called the Saffron Project. And it's about making secure multi-party computation tools for social science researchers. So again, like a motivating application is you have a lot of schools that have information about their students, and you want to compute statistics. You want to be able to run linear regressions or crosstabs or something across different schools to find trends in, say, academia, or across different companies to find trends in salary or something like this. And you want to do that in a privacy-preserving way without the schools being required to give their data to any centralized computational party. And So one of the problems that's been a barrier to adoption of secure multi-party computation is that you essentially have to build everything from the ground up. In the past, there have been a lot of tools where people have said, I know, let's take this very specific application and we want to run exactly this linear regression, and we'll build you a secure multi-party computation that runs this linear regression with this many parties on this type of data set. The idea of the Saffron project is to make a front-end toolkit that would allow social science researchers or government researchers or analysts of any kind to use the secure multi-party computation in the way that they would with a traditional statistics package. So the idea would be that the underlying secure multi-party computation is very flexible in terms of the number of parties you're using or what their databases are, how their databases are stored, or whether you want to do this kind of regression or you want to do a crosstabs or you want to do something else. But to give researchers who aren't familiar with secure multi-party computation front end that looks pretty similar to the kinds of languages they've been using and allows them to do the kinds of statistical computations they would want to do without requiring anybody to share any of the underlying data. This is a challenge. We've been working with statisticians to basically rebuild a lot of the underlying statistics functionality of traditional statistics packages to rebuild those on top of a custom secure multi-party computation backend. The idea is basically just really about improving usability. I think that's a place where there's a lot of room for cool stuff. Things that I'm not specifically working on, but I think has been a really nice application of secure multi-party computation is in the decentralized key management. And there's a company, Unbound Tech, which uses secure multi-party computation for ideas like this. One is in password storage. Every website you visit stores your password, and for security reasons, they don't store your password in the clear. They store a hash of your password. And going back to deterministic versus probabilistic, the hash of your password is a deterministic function of your password. And Amazon has a list of the hashes of every one of its customers' passwords. And when you log into Amazon, you provide it with your password, and then it hashes your password and it compares the hashed password to the list of hashed passwords and see if it matches. And it can compare this because hashes are deterministic. So when it hashed my password before, it will get the same hash as when it hashes my password when I try to log in. And the reason it hashes these passwords is so that if somebody breaks into Amazon servers and they get access to their database and they download the list of everybody's hashed passwords, they don't have the raw passwords in the clear, so they can't immediately log in as you. But once they have the hashed password list, they can still run brute force attacks. And that's why it's important to have a long or complex password, because since hashing is deterministic, they can immediately hash every word in the dictionary and see what those hashes are and see if your password hash matches any one of the words in their dictionary. And if so, then they know what your password was. They've reversed the hash, and they can do that because it's deterministic. Now, the question is, how can you have something where you can log in but not have a centralized password repository? And one way to do that is actually using secure multi-party computation, which is you essentially split these encrypted secret shares of your password across multiple servers, and you need all of the servers to cooperate together to be able to reconstruct the password. Now, say Amazon splits their password server up into 3 servers. And now when I log in, those 3 servers do a secure multi-party computation to compare my password to my password, which was stored in a distributed fashion among these 3 servers. And now this is where collusion resistance comes into play. Those 3 servers can be running a secure multi-party computation protocol that is secure against 2 out of 3 collusions. If an attacker breaks into even 2 out of 3 of those password servers, they learn absolutely nothing about the underlying password list. You've now really increased the security of the underlying system because a hacker has to compromise separately all 3 of these password servers before they learn any information at all. And one of the things that's nice about this is the actual computation the servers have to do is actually a really simple computation. It's not something complicated like calculating the probability 2 satellites are going to collide. They're just trying to calculate if 2 strings are equal, right? If the password that I provided is equal to the password that's stored in an encrypted fashion. This computation is really very efficient. There's basically almost no overhead for doing this under secure computation. You can do this really quickly, and you get a pretty big privacy benefit from this. This is, I think, a very cool application. It's like a nice gateway application because it's the lowest level of things you can do with secure multi-party computation that gets you a big benefit, but doesn't require like a complex implementation of secure multi-party computation. And then the analog of this in the blockchain space is actually about storing the secret keys for wallets on a blockchain. And this is a big problem since blockchains were developed, which is if you have some Bitcoin, anybody who has access to your secret key can spend any of your Bitcoin, and there's no fraud protection in Bitcoin, right? By design, Bitcoin was designed so that you cannot reverse a transaction. So if anybody gets hold of your secret key for a second, they can drain your wallet, and there's no helpline you can call and say, quick, cancel that transaction. I didn't make it. It wasn't me. Please refund my account. Like, that doesn't exist. And it's actually really scary to hold Bitcoin funds. And if you're something like an exchange, you can't just write down your secret password and lock it in a vault and never use it again, because every time you want to use that wallet, you need that secret key. You can't keep your secret key in cold storage. Exchanges have these things where they have a hot wallet and a cold wallet, and the cold wallet is mostly offline, and the secret key isn't used very much. But the hot wallet, that secret key has to be in memory somewhere, and it's being used a lot. So that's something that's a real target for hackers, because if they could ever grab that secret key, they could just drain the exchange's hot wallet immediately. Here you have this issue, which is that you need to have the secret key accessible so you can sign transactions, but you're worried that it's a centralized risk. A hacker who can get access to this can really drain your account. So you can do the same kind of thing, which is you take your Bitcoin secret key and you split it among 3 servers or 5 servers or 10 servers. And now I can guarantee that as long as one of those 3 servers remains uncompromised, you learn nothing about my secret key. And now every time I want to make a transaction, I need all those 3 servers to engage in a multi-party computation that takes their private inputs, which are their shares of the secret key, and computes a joint signature using that secret key. These are being developed now and being rolled out. And this is like one of the simplest applications of secure multi-party computation that immediately gives you a big privacy boost.
Excellent. Brett, this has been phenomenal having you on the show. It's been so exciting. If people want to learn more about you or the research you're doing, where can they find it?
My website at Penn is probably a good place to start. And if you Google my name, Brett Hemenway Falk, my Penn website should come up first. And it has a lot of references about the papers that I've written and some of the stuff that I'm doing, the stuff that my graduate students are doing.
Excellent. Thanks again. It was great to have you on the show.